Hi, everyone in person, and hello to everyone online. My name is Kunal Vaishnavi. I'm a software engineer at Microsoft. And today I'll be talking about inference optimization with Model Builder and ONNX Runtime GenAI. So a little bit of background. What's the typical way people traditionally get models from, let's say, PyTorch to an optimized and quantized ONNX model state so that it can be performant and shipped to production? Well, first you'll take your original implementation, maybe it's in PyTorch. You'll export it to ONNX. Maybe you'll use the torch script export. Maybe you'll use the Dynamo export. After that, you'll get an unoptimized ONNX model. You will then want to identify common subgraphs that you can pattern match against and simplify so that you can reduce the graph into less operators, and those operators that you can insert that replace the subgraphs that you're taking out can use more optimized kernel implementations under the hood to run the model. So maybe you're using the ORT transformer optimizer, or you're using the ONNX rewriter to optimize your ONNX model. And then you'll want to quantize afterwards to reduce the model into lower precision so that it can fit, let's say you're deploying on device. So maybe you're using the ORT quantizer scripts for that. And that's great. That's a great process to get the final ONNX model. And during this process, we see a lot of common optimizations that are done. And these common optimizations are commonly seen across a wide variety of models, especially these LLM-based models that are coming out now more and more in the GenAI era. So things like layer norm or simplified layer norm, skip layer norm or skip simplified layer norm, rotary embedding, multi-head attention, group query attention, and there's many, many more. And when we have these optimized contribops in our ONNX model, there might be many, many types of variants. So if we take attention, for example, there's many types of attention. There can be multi-head attention, packed attention, sliding window attention, multi-query attention, group query attention, and the list goes on. And for each of those operators, it can have multiple different kernel implementations under the hood to run the actual calculations. So algorithms like memory efficient attention, flash attention v2, scale dot product attention, and the list kind of goes on. And what we notice across a lot of these models is that they share a lot of the same core blocks. So once we've done this entire pipeline, and we get the final optimized and quantized ONNX model, we'll see it has a layer norm or a skip layer norm. It has a rotary embedding. It has an attention op, and it has some sort of MLP structure. And more often than not, if we take a PyTorch model and we export it to ONNX, whether that PyTorch model was using an optimized implementation of attention or if it was using eager attention, let's say, source code improvements that are made in the original modeling code are usually made within those core blocks and don't affect the inputs and the outputs to that actual core block. So if we take attention, for example, you'll still have your QKV matrices as your input, and you'll have the output matrix for attention as your output, no matter whether you use eager attention or scale dot product attention or flash attention v2. So even though these source code changes can accelerate these core blocks as computations, it doesn't actually change the inputs and outputs when we look at the final optimized ONNX model. And so we can take this a step further, and so when there's a lot of abstract tools out there like Microsoft's Olive or Hugging Face's Optimum that'll use these core tools under the hood to get you the final ONNX model, and more often than not in the LLM space especially, the final ONNX model produced across all these combinations is the same. We can even take that a step further and say, we look at, let's say, a lot of the popular LLMs. So in the top left, actually I'll go on this side to make it easier to point. So in the top left, you can see Llama 2 7 billion. Typically, it's structured as some sort of input layer norm, a group query attention, a post attention layer norm, and an MLP layer with up-down projection style for 32 layers, let's say. Now, if we look at Mistral, the only difference really is that the sliding window attribute is enabled for the group query attention operator. If we look at, let's say, Phi 2, post-optimization, quantization, and all that, the main difference we see is that partial rotate equals true is enabled for the group query attention operator, and the MLP layer might be the fully connected style instead of the projection style. And then even if we look at, let's say, Gemma 7 billion, it's pretty much the same as Llama 2 7 billion. The difference is just the number of layers. So the final ONNX model across many LLMs is very similar, if not identical, besides the weights that are used. So if we know what the final ONNX model should roughly look like, why can't we just kind of go from our original source model to that final ONNX model and kind of skip all those intermediate steps since we know what the final output should look like? And that's kind of where the model builder comes in. So it's a new way to automate and simplify this pipeline, and it uses common building blocks to directly create the final ONNX model. And it builds for various precisions, different EPs. So if we see on the list here, we've got full precision, float 32, bfloat 16 precision, which was recently added, float 16 precision or half precision, int4 for quantized precisions, and most recently, we integrated kquant, which is an algorithm from llama.cpp, into the model builder, so now we can produce int4 plus int8 mixed quantization. And it also builds for a wide variety of EPs as well, so CPU, CUDA, DML, NVIDIA's new TRT RTX EP, ROCm, Web GPU, and we keep adding more EPs as we go. Excuse me. The final output ONNX model from the model builder can run directly in ORT, ONNX Runtime, ORT GenAI, ONNX Runtime GenAI, and Hugging Face's Optimum with no additional work. What that means is, if you want, you can pass in your final input model, your execution provider that you want to run on, the target precision you're looking for. Once you feed that information to the model builder, you'll get your final output ONNX model, and that ONNX model will be performant enough to run directly on any one of those products. You can choose to do any further post-processing if you want, but the final output ONNX model should be pretty much performant on a wide variety of EPs. The model builder supports a wide variety of inputs, so you can take in a full precision, half precision, quantized PyTorch model. We also support GGF models, and we can convert those to their equivalent ONNX representations as well. And the way that the model builder is designed, we can extend the ability to use future different types of input models, such as, let's say, TensorFlow models, and easily onboard them to the model builder, because the way it's structured is the model builder is treated almost like an IR, where as long as the input model is defined with certain class attributes, we can read those class attributes and then create the ONNX model accordingly. And so you can think of this as our competitive solution to llama.cpp. So how do you actually use the model builder? So down here below is kind of an example of the CLI usage. So if you install the ONNX Runtime GenAI package, you just do ONNX Runtime GenAI.models.builder. You can pass in the model name that would be in Hugging Face, or if you have the model on disk, the path to the local folder on disk, the output folder that you want to store your model and weights in, the target precision, and the target execution provider. So how does the model builder actually work? So model architectures are implemented as classes of predefined graphs, and these graphs are composed of common building blocks. So if we look over here on the left, we can see llama 2 7 billion is defined as follows. You call the make layer norm method to make the layer norm. You call the make group query attention to make the group query attention afterwards. You call make layer norm again for the post attention layer norm, and the make MLP to create the MLP style with the projection equals true setting turned on to have it be the up-down projection style MLP. If we look at Mistral 7 billion, the only difference now is that we turn on the window attribute and set it to true to enable sliding window attention. If we look at, let's say, Phi 2, now we just turn on the partial rotate equals true setting for the make GQA, and we turn on the fully connected equals true setting for the MLP layer to make the fully connected style. And for Gemma 7 billion, we use the same settings that we did for Llama 2 7 billion, and the model builder can detect the number of hidden layers that it needs to process to create the final ONNX model. So here are some examples of functions and attributes in the model builder. In the top left, you can see the highest level, or higher level abstraction, I should say, where you can see make layer norm for the input layer norm, then make attention for the self attention, make layer norm again for the post attention layer norm, and the make MLP for the MLP layer. Below that, you can see an example of how you would make the GQA node itself. Not too many lines of code to actually insert it into the graph. And then on the right is an example of how you'd make the MLP projection subgraph. So you just create the 3 different map mulls, your extra mull node. If there are bias nodes for the adds after the map mulls, that's also handled for you. And then down below, you can see here how you can kind of turn on and off these settings in the attributes dictionaries. So in the layer norm dictionary, you can see simple is defined as true by default. So if we turn that on or off, we'll get an RMS norm versus a regular layer norm. Whether it's the first or last layer norm can be tracked. And global information that needs to be tracked as the model's created can also be stored in these attribute dictionaries. So things like the root input or the skip input or output 0 or output 3 can be tracked in these attribute dictionaries as well. And then on the right is basically a similar example, but for the rotary embeddings. So how do you actually contribute to the model builder? So this is the full PR diff for actually adding the Gemma model. In this case, what we do is we inherit from the Mistral model architecture that was already onboarded, and we try to see, okay, what are the new features that are different in Gemma that we didn't have before in Mistral? So in Gemma, we have a unit offset in the layer norm, and we normalize the embedding output. So at the top, you can see the normalize setting is turned on to true, and the add offset is set to 1 to do the add offset. And the addition of those settings in the attributes dictionaries is in the screenshot below. And to the right, you can see the actual graph changes that were made. And the top right, you can see the add offset done on the layer norm weight. And then below that, you can see the diff for adding the mul node after the gather node, which will compute the embeddings to normalize the embedding output. So it's not that many lines of code that needed to be changed. In this case, I think it took about an hour, and now we suddenly have a fully optimized and quantized ONNX model across a wide variety of precisions and EPs. So what are some of the benefits of the model builder? Well, it scales pretty quickly and easily to support a lot of these new models, especially in the LLM space that come out. So models in an architecture family like Llama or Mistral can now be fully supported out of box with little to no human intervention. In some cases, I think earlier today I was told there was a Llama model that came out from another company. It was not a fine-tuned version, but some parameters were slightly changed. And I didn't even know it existed, and it was fully supported via model builder out of box. So that was amazing to hear. Fine-tuned versions are also automatically supported because it's just a simple change of the numerical weights. It's pretty easy to add new model architectures. You just use class inheritance to reuse existing architectures' work, and you only need to basically make the changes that are unique to your new model's architecture. So as a result, it reduces the amount of dev time it takes to produce the final ONNX model from, let's say, weeks or months to hours or just days. There's also no export failures or graph fusions that need to be maintained. So if you have issues that you run into during export or optimization, you don't really run into those here with the model builder. It's not using any of the core tools like the exporter or the ORTs or ONNX scripts, optimizers and rewriters. It's just using, at the moment, ORTs quantizers to do the quantization step. As a result, it reduces a lot of the version dependencies that you see in a lot of tools on other packages. Currently, I would say the core dependency is A, the ONNX runtime quantizer, and B, Hugging Face's transformers. And one thing I want to clarify there is that with Hugging Face's transformers, you might think that modeling code changes from version to version might impact the model builder. But the way that the model builder processes models is it cares about the loaded model's class structure. So the attributes that are defined in the class are what we care about more, not what the forward pass is defined as. So if you take something like an attention, you're always going to have a Q projection, a K projection, or a V projection, and that's not going to change from version to version. So even if the modeling code changes from, let's say, flash attention 2 to flash attention 3 by default, that isn't going to impact the model builder's ability to convert the model to ONNX. As I think it was mentioned earlier today, model builder is also accessible through Olive as a pass, so you can leverage it there. And a nice added bonus is that you can build mini models for testing. So if you've ever run into a situation where you want a one-layer ONNX model just for debugging purposes, or a two-layer ONNX model, and you have to typically author that by hand, you can use the model builder to directly create that for you. There's an extra options flag that you can use and turn on the num hidden layers equals whatever number you want. So the bottom diagram is trying to show basically that you get the final PyTorch or the final GGF model, and you can use the model builder to build that final ONNX model that you'll get. So this is all great, but how do you actually run the model, right? So typically, if you're using ONNX runtime by default, you've got quite a lot of code to write. So on the left here is the first part of the while loop, or the generative loop, and the second part is the same loop, but right below it, the length of the code is so much that I had to put it into two different pictures. And this isn't even the full code snippet that I can show. So there's things missing like tokenization, detokenization, going back in context and history, and other features that you might want to use in your generative AI applications. And so you might use another solution like Hugging Face's Optimum, which kind of cleans up the code and makes it a lot simpler to work with. And you might have something like model.generate to kind of summarize all that while loop and logic that's happening in there. But the problem is that solutions like Hugging Face's Optimum are not running optimally. They'll run the ONNX model using ORT's backend, or whatever provider you're giving to Optimum. But search and sampling are still going to be running on the CPU, or it'll be running in PyTorch, and it won't be running as efficiently and leverage ONNX Runtime's technology to run more performantly and even on device. So what can we do about that? Well, we could write a generic inference script per model. We saw the ORT script, we saw the Optimum script. We could use that and try to make that more generic. We could also try to wrap the generation logic in an op. So in ORT, you might have seen previous iterations where there might be a beam search op or a greedy search op, or sometimes there's even model-specific generation ops like whisper beam search. Or we could use another solution to handle the generation loop. And that's where ONNX Runtime GenAI comes in. So it's basically generative AI extensions for ORT. It's also cross-platform, available on many devices, and it has many language bindings, just like ORT does.